there's one final property that has sort of dual use both for linear maps and for matrices, and that's the property of being singular or non-singular. So for a linear map, we call a linear map non-singular if it's one-to-one and onto. So this is how we'll use the term. Some people leave off the requirement that it be onto, but we'll go with the flow and define it this way. Notice that, of course, if you have a linear map that is one-to-one and onto, really you're talking about an isomorphism. So using this definition, non-singular is really just the same as being an isomorphism. If your linear map is not non-singular, then it's called singular. So it might be not one-to-one, or it might not be onto. There's a corresponding. There is another use for the word singular for describing matrices, and we call a matrix non-singular if this matrix equation has a unique solution for every possible vector b that you could put on the right-hand side. Now remember that this matrix product ax equals b, this equation really represents any linear system. That's one of the nice things that you can do with the matrix vector product. You can express any linear system as a matrix times a vector equals some other vector. Notice that for this equation even to make sense, if a is m by n, then x had better be n by 1. So x is actually an Rn. And the product, right, the product sort of uses up the adjacent things, and the result is that b had better be m by 1, and so b is in Rm, right? So we call a matrix non-singular if this equation, which is a stand-in for a bunch of linear systems, always has a unique solution, no matter what vector is on the right-hand side. If there isn't always a unique solution, either because sometimes there's no solution or sometimes there's more than one solution, then we call the matrix A singular. Now, of course, because both of these words, singular and non-singular, get used for both linear maps and matrices, you would hope that there's some correspondence between these. In fact, you would probably hope that a linear map is non-singular exactly when the representing matrix is non-singular, and vice versa, a matrix that is non-singular produces a linear map that is non-singular. And we'll see that this is the case. So if F is non-singular, that means that the rank of F, well, it means two things. So first of all, right, F is from V to W, so if F is non-singular, since F is an isomorphism, that means that the dimension of V has to be equal to the dimension of W, right? So the corresponding matrix, rep BD, no matter what bases you choose for V and W, the representing matrix will be square, because it has to have this many rows, but this many columns, but those are the same. So let's call these both n. So it has to be n by n, right? On the other hand, we know that the rank of F has to be n because it's onto, so the dimension of the image has to be the dimension of the codomain, so that's n. But also the nullity has to be 0 for two reasons. One, because of the rank nullity theorem, but also if F is 1-to-1, then the dimension of the null space had better be 0, so the nullity is 0. Okay, so now let's think about what both of these things say about the representing matrix. Well, if the rank of F is n, we've seen that the rank of F is equal to the rank of the representing matrix. So that means that the rank of this representing matrix is also n. But for matrices, we know, right? We know already that this matrix is n by n. For matrices, we know that the rank of a matrix this should be an F here, plus the number of non-pivot columns has to equal the number of columns, n, right? Well, if the rank is n, then that means the number of non-pivot columns is 0, right? So that means that if you write this, any linear system like this, when you do row reduction, you have to end up with a pivot in every column because you only have n columns and you know you have n pivots because the rank is n. So you get 1s down the diagonal like this, and that means that you get a unique solution, right? So we've shown that if you have a non-singular matrix, the representation is, if you have a non-singular linear transformation, the corresponding matrix is non-singular. So now let's do the reverse. Let's suppose that we have a non-singular matrix. Does that mean it produces a non-singular linear transformation? Well, so saying we have a non-singular matrix, that means that this has a unique solution for all B. Okay? In other words, when you row reduce this, to get a unique solution, well, a couple things have to happen. First of all, for this to always produce a unique solution, for this to always produce a solution, no matter what B is over here, to always produce some solution, you have to have more columns, at least as many columns as rows, right? So this is for a solution to exist. All right. For a solution to be unique, you have to have at least as many rows as columns, right? And this is because, right, if you have too few rows, you're guaranteed to have a free variable, but then you won't have a unique solution. So for solutions to exist, for a solution to guaranteed to exist, we need this. For a solution to be unique, we have to have that. Well, so if solutions are guaranteed to exist and be unique, that means m has to be equal to n. So in other words, our matrix is square. So since A is non-singular, that means, among other things, it means A is square. It's n by n, right? So now let's think about this linear map that A produces by going from x to ax. What is the rank of this map? So to give this a name, let's call this f. What is the rank of f? So this is from Rn to Rn, right? Well, the rank of f is, because we said that to have unique solutions, you have to have ones, when you row reduce, you have to have ones down the diagonal. So that means that the rank of f, well, the rank of f is equal to the rank of A. But if there are ones down the diagonal when you row reduce, that means the rank of A was n. But now we have the rank of f is n. So the rank of f, we know the rank of f plus the nullity of f is the dimension of the domain space, which is n. Well, if the rank is n, then there's sort of nothing left for the nullity. The nullity has to be 0. So the nullity of this is 0, right? But that means that f, this function f, that's really just matrix product with A, is 1 to 1. But since the rank of f is equal to the dimension of the codomain space, Rn, this means that f is onto. So this shows that if we started with a non-singular matrix, the resulting linear transformation is one-to-one and onto. In other words, it's singular. So this shows the other way, right? That's non-singularity goes that way. So singularity and non-singularity for matrices and corresponding linear transformations mean the same thing.